Thanks everybody for tuning in today. This is Bill Schlund, and I'll be going through advanced simulation in Creo. I'm going to go through a couple of PowerPoints at the beginning to set some of the concepts and what's unique about it, and then I'll be going through some examples because there's a lot of different things you can do with advanced simulation. But first of all, kind of where does it sit in the field of analyses products that Simulate has? So out of the base kind of bundle, there is something called Simulate Elite, and that allows you to do linear static analysis. And then it's some of the higher level bundles, and you can also, obviously purchase that on its own, but regular Simulate will do all of what EACPDS does, or Simulate Elite, and then it will additionally allow you to do modal buckling analysis, steady state thermal analysis, and then design optimizations, and also some instances of contact. But what our focus is today is the advanced simulation extension, and that's going to allow us to do everything I've mentioned so far. In addition to that, we can do some finite element idealization, so some different types of elements to approximate certain situations and make things maybe a little bit more efficient. Also, some nonlinear materials and large deformations, dynamic and pre-stress analysis, and then nonlinear and transient thermal analysis. So we're going through, like I said, a variety of different examples to kind of cover these. I want to touch on each one just a little bit deeper dive. So the capabilities in the advanced simulation as far as idealizations go and the like is there's an idea of composite shells. So that would be for a laminate layup. We have different materials and different orientations laid up on top of each other. There's also nonlinear springs. So Hooke's law says that springs are linear if we go according to that, but this also will deal with nonlinear springs. And then we'll also do crack and fracture mechanics. So here's an example. You can see an image down here where we have a crack in a material, and then it's being under stress. We can kind of see how it separates here. And then there's something called weighted links. And weighted links is just a way of kind of an interpolation entity that allows you to take the mass or loads at a single point and then apply that to target geometries. So again, it's a way of kind of simplifying things without putting in other parts to represent that and put those in that way. So for nonlinear analysis, Simulate is still a linear solver, but it can do nonlinear analysis by using a process where basically all the external loads get applied in steps. So the user defines how many steps they want the analysis to go in, and it basically runs it that many times. And then after each step, the model geometry updates to the deflected state. So for instance, after step 2, it deflects a little bit. Step 3 runs on that deflected state and continues to deflect it even more. So that's really how we do large deformations, and then also dealing with elastoplastic materials and hyperelastic materials. We can also do varying loads over time, and certainly large deformations over a variety of different types of products, whether they be thin or regular type products. And then nonlinear contact with infinite and finite frictions. The next thing I want to talk about in capabilities is the dynamic or the pre-stress analysis. So pre-stress would be if we had a couple of plates bolted together and we torqued those bolts down to 90 foot-pounds. That actually influences the behavior of those plates as they go under stress. So it can take into account, and that would be considered pre-stress, and so it takes into account those types of situations where it actually, that stress, pre-existing stress, does affect the behavior and the response of the product being analyzed. And then also we can do some frequency response and also get results over the frequency, any frequency that we define, and also over different time intervals. And then finally, on the thermal end, I mentioned that does nonlinear thermal analysis. So kind of temperature dependent convections. It'll also do radiation, and then temperature dependent material properties. So the material property might change depending on the surrounding temperature. And then time-dependent boundary conditions, as things change. We'll go through kind of an interesting example of that. So with that, I'm going to minimize our PowerPoint here, and then let's look at Creo. So the first example that I want to go through is a large deformation analysis. And really what we would consider large deformation is if a part deforms more than the thickness of that part. And so here we have a buckle. This is typical what you might see in a backpack or a belt or something like that, where you have the two plastic ends and you kind of push them together and snap them into kind of the female side. What I'm going to do is just look at a part of this so that it will solve a little bit faster. And so we'll work on just this portion of the buckle. And we'll take a look at this again. This would be considered a large deformation because we're actually going to push this down quite a bit. And that's what it's meant to do. So let's take a look at this. We'll go under simulate, and we can see we already have some things set up here. So we have constraints on the back, locking this in. We have symmetry constraints down here. Remember, because I cut it in half, so it's just using symmetry constraints where the rest of the part would be. And then we have a load right here. And if we take a look at it, we can see that, we have a couple, and this is measured in newtons, but basically we're pushing on this with about maybe 2 to 3 pounds, right? Pushing it down with our fingers or a thumb. And so with this, we want to run an analysis. So I actually ran it twice. I ran it once as a linear analysis, just like you would in regular simulate. And then I did another analysis with large deformation. So we'll take a look at both of those. But if we go under the analysis, here we take a look at the linear analysis. If I just go and say, let's take a look at that, we can see it's using the constraint sets that we saw before, where it's locked down. We got symmetry constraints. And then the load, right? We're pushing on it with that 3 pounds. And so just regular simulate would run through this, runs and solves it really, really fast. PTC has owned the source code for simulate for about 26 years, and they've been tweaking it all the time. So it is an incredibly fast solver. And so the other analysis that I ran here is for large deformation. And so when we look at that, there's a little bit different where I picked up here, because I have the advanced simulation package, I can choose nonlinear and calculate large deformations. So instead of just taking the constraint set, it's also going to do the constraint set, and I can drive it using a table or some kind of formula or something like that. In this case, we're just going to use the default, which is a ramp function. And all that just means is that it's just going to consistently, it's a slope of 1 type of a graph, right? So just a straight line. And then also with the same with the load set. So the only difference here then, besides using these default simulation, or I should say functions, is I look under here under output. And this is what I mentioned before, where we take a linear solver and have it solve nonlinear situations, is we have a number of steps that we have, and it's going to run this, in this case, 6 times. So we've kind of spaced out the load over 6 intervals, and we're going to run that analysis 6 times to take a look at that. So let's take a look at the results, and I'm going to put them side by side so we can take a look at them and kind of see the differences there. So the first one, we'll pop it up here. Remember, is the linear analysis. So we can see the deflection here, pushing on it with, about 3 pounds, 2 or 3 pounds. It's moving about 3.5 millimeters. So that's not too much. And if we assumed that we didn't have large deformation, we would think, well, maybe we got to change this design, use different material, get a stronger person to push on it, because this isn't going down far enough to click into the other side. But if we use the large deformation, we can see that there's quite a big difference compared between 3.5 and 10.5 roughly millimeters. So this is a much more realistic of what's happening. And again, this is designed to deform like that. So this is a large deformation situation here where we can do that. And here we can get the accurate results of what's happening there. So this is just a large deformation. As you can see, we just set it up to run it a number of times. We pick the number, how many, more than one, obviously. But the more we have, the more accurate it will be as it goes along, but you don't want to do hundreds and hundreds, but a fair amount, and just to get an idea of what's happening there. So let's close this out, and we'll close out our window here. We'll go to another example. So in this example, I have a metal plate here, metal plate here, and I got some urethane in the middle, right? So something that kind of stretches and moves, certainly much more than what steel does. And what we're going to do is take a look at this. Going into simulate, you can see that it's being locked down in this, so it's like basically bolted down. And then in this area, we're putting on a load, and we're pulling it with about 70 pounds, a little bit more than 70 pounds of force, kind of at an angle like this. So in this case, again, if we were looking at the analysis, we could just run a linear analysis. And if we take a look at that, it's exactly what you say. It's using the constraint set. Remember, it's bolted on that one end. It's using the load set. We're pulling on it with about 72 pounds of force. And that's it. It goes and solves it. But now the next one we want to do is take a look at it with really hyperelastic material. And before we do that, let's look at how we get to something like that. So here's the material of this that I'm using here. This is using regular, steel material. But here, I'm going to say, let's take a look at this guy. And you can see that it's urethane. I'm going to say, let's give us some more information on that. I'll say, let's look at his properties. So here's the urethane, and we can see there's a variety of properties here. What we did is we changed it from typically, this is always using, the stress strain is using linear, but in this case, we're using hyperelastic because this is going to stretch quite a bit. So we're using that. And when we do that, it says, well, how do you want to determine that behavior? And we just go under edit. And what we did is we ran a series of tests. So these are the test results. And here is what the way that it deforms. This is the stress strain curve for this material over a series. And we can see that it's a nonlinear response. Not hugely nonlinear, but it is nonlinear. So it does behave differently. And so there are a variety of different techniques or models that we can use to approximate this. So there's a Mooney-Rivlin. And so we can look at each one of those, and we pick the one that best fits our point representation, the different results that we have here. So this one gets pretty close, but we can do the Neo-Hookean. So this is kind of the hyperelastic version of the Hooke's law. And we can see that that follows again, kind of close, but not exactly. We could take a look at polynomial order number 2. Looks like this. Again, not real close. If we look at Yo, you can see that's quite a bit closer to what we want to do. So this particular modeling method will work the best for the points that we received in our test results. So I'm going to have it use that when it does that. So that's how we specify a hyperelastic material, is usually through a variety of test results. And then we fit one of these modeling, basic modeling, mathematics to approximate that. So that's really how that's being used. So now if we go back and take a look at our analysis here, we'll look at the static analysis, or the hyperelastic analysis. Again, we're doing it over a ramp, but it's making use of that hyperelasticity. So we're saying it's a nonlinear situation. In this particular case, we want you to look to hyperelasticity, which is again going to follow that Yo analysis model that we chose. And again, also because it's nonlinear, we're going to choose a series of steps. In this case, we picked 9. So it spaces it out over 9. So it's going to run this 9 times. So again, looking at the results for this, I'm just going to go in and say, let's look at the results. Here we can see the linear. So we can see the deformation here. Here we can see the nonlinear, right? So this is taking into account those test results that we got. And one of the things we could maybe do is say, let's tie these two together, right? So now they're basically using the same legends over here. And then additionally, we could go in and say, let's tie their orientations together. So now when I spin one, we can spin the other. But we can see dramatic difference here between using a hyperelastic material and being able to model that correctly or analyze it correctly, as opposed to a linear analysis. So again, like we saw with the large deformations, we can see that with hyperelastic materials. And it's really pretty simple to set up, right? It's a very easy problem. So the next example I want to go through, and we'll go into the thermal world at this point. Here we have a weldment, and we have a weld between, these components and the base component. And what I want to do is simulate that weld being put in. So I'm going to go into analysis, and what we're going to be able to do is on the simulation side in thermal. So you notice the menus are different now because we're using thermal. So we have different things, instead of loads, we have heat, we have prescribed temperatures, convection. We also remember, because we have the advanced simulation model, we can also use radiation if we chose to do that. But what I'm going to do is, let's take a look at the load. So instead of being a force load, it's actually a temperature load. We're going to go over here and take a look at the loads. And we're going to say, let's take a look at this guy. And what we're using is actually a function. So here's the, in watts, right, what that heat or heat load brings. But then we're using a function, and we're basically, you can see here, it's kind of highlighted in the green curve with the arrows. So it's going to start here and move it along this curve and come out the backside over here. So this is how we're going to simulate the welding process, is that weld, as it's creating the bead, is going to move along here, go along this edge, and then come back out. So it's actually we're going to see that happening, and we're going to get to see the temperature changes as it moves over that. So let's go to our analysis. I'll say, let's open up, and we'll say under display, we'll say, let's animate that. So it's creating the animation frames for us here. I think it is. All right. Let's try calling him up. So we won't save that guy. So here we can see the weld bead going along here. We can also see how the temperature changes. You notice that it holds temperature a little bit longer here than other places. That's because there's no material on this side to pull the heat away, so it stays that way a little bit longer. But here we're being able to simulate this running along that path with that 3,000 or 30,000 watts that was there. So very kind of an interesting way of doing thermal analysis and seeing how things change over time. Let's close this guy out. The next thing, we have another example. In this particular example, we're going to take this pin and push it into this component. It's going to ride up on, basically this is acting like a spring here. So it's going to push this down. And then because of the spring force, it's going to lock this guy in place. So basically we push him in and then he's held in place. And this is kind of a small model. One of the things I did is I'm not going to actually use a force to push this pin in. I'm actually going to use enforced displacement. And all I'm going to say is, let's move the pin from where it is now. Let's move it 1/8 of an inch forward, and we'll watch how the rest of the product behaves and interacts with that. So let's go in and take a look at our simulation analysis. So when I do something like this, this is going to be using contact, right? So obviously this pin isn't touching anything right now. If we can zoom in here, we can see it's just kind of floating in space, but it will move in and eventually come in contact with this guy and push him down. And then actually the bottom part of this is actually going to come in contact with down here as well. So there's all kinds of things taking place here. And we can define what kind of friction we have between these two components and things like that. If we wanted to take a look at how this is set up, and it's actually really easy to set up, is we just use contact between two surfaces. So right here, I've picked this base surface, and I'm saying it's contacting this surface here, and eventually it will as it pushes in. Right now, they're not touching. So when we specify the interface between two components, we can say that there's contact. They can be free, right? So they're independently, it can basically go through one another. One does not see the other. Or we could say they're bonded. They have to be touching and they stay touching. So we're using this contact option, which does that, allows those. So not only, and it's always in pairs, right? So I do this surface touching this one, and then I'd say this surface touching the top one up here. And then I'd say this front surface, this guy touching this guy down here, and so on and so forth. So I'd make a couple of pairs. And then I actually did a surface between this guy and the underside of this thing here. So a number of contact regions that are being selected there. And then again, the enforced displacement are just pushing this forward. Other than that, and then this brown part is basically just locked in the back, right? So he doesn't move at all, up or down or anything like that. So if we take a look at this analysis, just to kind of review it here, we can say that we're using calculate large deformations. We're taking into account contacts, right? Because two parts are going to be touching each other and affecting one another's behavior. Again, as far as the constraints go, it's just, we could just say it's ramp or it's not moving at all. There is no load set, right? There is no load here. I'm just physically moving this forward a certain distance. The one thing you need to do is this little button right down here, this little checkbox, say press fit. And what that does is it helps it get to an answer. And it also, when I first ran it without that, this pin, kind of went right through the regular part here. But when I check the button saying press fit, it helps it analyze it and also come to an answer. So again, under output, I also went in here and said, let's run this, in this example, like 41 times. So what we're going to simulate is this guy. And as you can see, if I pick on this just to review its enforced displacement, we can see that it's right there. We're moving it in. And actually, we're moving it in 0.135 inches. So that's how far it's being moved in. Okay. So looking at the results, you see this being pushed in. We can see the other part moving down. When I ran this, it actually gave me a message saying, as a warning message, that slippage is taking place. And it definitely is, right? We can see that right here, that this part is sliding. It hits, comes in contact, and then it slides a little bit more. So it lets you know that these things are happening, but we can kind of see this going through and simulating how this would work. Okay, so up until now, we've been going through some different examples. I wanted to go through one with you by going through all the picks so we can see how to do something, and a different example, right? Something we haven't done yet. So here I'm going to do plasticity. So plasticity is where something bends and stays bent. Like if you were to bend a coat hanger or something like that. In this particular case, we're using this as a staple. It's being pushed down. The ends will ride along here. It will bend this, and it'll stay bent. So basically, this is our staple. This is kind of the base part that it will ride along. And we're going to go and do this type of simulation. So let's go into simulate. And first of all, we have this base part just locked to the ground, right? It doesn't move. It's fixed in all degrees of freedom. Now the staple itself, just like we did with that pin example we just went through, if I take a look at him, he's actually being pushed in the Y direction, which is downward, right? It's being pushed down this way towards the base. And this is basically just being used as a vector. I'm going to actually use a table to drive it down and then move it back up again. So we've got at least things set up from a constraint standpoint, but we don't have any materials in here yet. So I'm going to go in and say, let's go in and assign a material, and we'll just use regular aluminum. So I have that to apply. I'm going to take this, I'm going to copy it. So now we have another version of this. And this one, I'm going to say, let's delete this. and we'll call it elastoplastic. So aluminum elastoplastic. And in this case, I'm going to come over here and say elastoplastic. So before we did the hyperelastic, remember we did that one? Typically, if we're in a linear world, we do linear, but we're going to say elastoplastic. Right away, it jumps to, okay, defined by tests, right? So what answers are you going to give me that I can use to represent the behavior that's going to happen? So I'm going to say, let's edit this. And this is where I can read things in. It'll show me a graph. So I'm going to say, let's read in an example again of tests that we ran before. So let's grab this. Let's see. There we go. Here's our text file. We want to use that. So here's a representation in the plastic world of how this behaves, right? And you can see it's pretty linear in this particular case. So we're going to use that. So now my material for the elastoplastic is using test results of a previously run analysis on that type of material, so we can use it to drive our part here. So now we have that defined. So now we can say, let's assign those materials. So I go over here, I'll say, we'll assign aluminum to this component, right? Because these are just going to be regular linear aluminum type part. And then let's assign our elastoplastic to this guy, right? With the test results in it. So now we've got our materials set. So we got our constraints, basically kind of our load, right? Because we're using enforced displacement. And then we have our materials set. So we're almost finished. The only thing that we don't have in here right now is these parts aren't touching each other. So again, like we saw with that example we just did before, we're going to have to do some constraints or some interfaces between these. So setting that up is really simple. We go into refine model, we say an interface. Again, remember, it could be free or bonded. In this case, they're going to come in contact with one another. And I just pick this surface under here. We always do it in pairs, and this surface there, and we say, okay. So I'm also going to assume that this backside might be rubbing along this guy at some point, just kind of cover my bases. So I'm going to say, let's also do an interface between this face and this one. And again, certainly we're going to say that that is in contact. So now we've got that interface done. And then we do the same thing on the back side over here. So another interface between here and here. And we'll say it's a contact. And then one last one on the back side between this guy and that guy. So now we have things set up. We've got our materials assigned. We're taking into account the contact of the two parts as they're going through this process. And finally, what we want to do is set up our analysis. So I'm going to go over here. Oh, one other thing is, because there's going to be some kind of large deformations and changes coming in this area, I'm going to put a little bit more elements in the corners here to maybe get me some little bit better results. So I can use something called map mesh, but basically I can control the mesh in a particular area. So I'm just going to say between this surface and this one, let's use like 4 elements. So 4 elements across and 4 through the thickness. And I can do the same on this side too. I'm going to say, let's pick this guy and the inside there, and the same thing, right? So now we've got a little bit more definition that we can derive from this. And again, if I say AutoGem just to mesh this, so we can take a look at it, look at the elements. You can see that, here we have our nice brick elements, 4 by 4 here, and then we're using the regular tetrahedrons along the rest of this. So hopefully this will give us a little bit better results in the corners, because there is going to be some things going on there. So now we have everything set up. We got good elements set up. We've got contact. We got materials, and we're ready to go. So let's go in and say create an analysis. I'll say let's create a new static analysis. Again, I'm going to click nonlinear. I'm going to say calculate large deformations because it's going to be a large deformation. Contacts, right, because they're contact, and also plasticity, right? So it's going to look for material plasticity and have that behave accordingly. So as far as the constraints, remember this bottom part, this base part isn't going to move at all. So I could use that ramp function like we did, but I'm just going to show you another thing that we can use. So we can go under functions, and I have a function under there just called a constant one, right? So if I wanted to look at that, and I could say, let's review it and let's graph it out. All it is a straight line, straight across here, that doesn't change, right? And that's basically what we're saying with this is that, you know, that part doesn't change at all. I want to close this guy out. So we're going to use him. Now the other one, the other function that we have is going to simulate this. We're going to push him down, he's going to bend, and then I'm going to pull him back up so we can look at him. So this is going to be a different type. And again, we're using a table for this, but I could say, let's take a look at this. This is our up down. And again, we can review this. Let's make a graph. So again, remember the vector was a negative value. So basically it's starting where it is. It's going to go down this distance, which is 5.8 millimeters, and then it's going to go back to where it started, right? And this is over the period of time that we're running this. So we can just, you know, and a linear representation is certainly an accurate way of doing that. So it's just going to move to a certain point, and it's going to move back to where it started. And that's all that's showing. Okay, so for the fixed stapler, we're going to say, let's change this to constant, right? So it doesn't, he doesn't move. And then for our staple top, we're going to use that up-down function. So using two different functions on here. There are no loads again, because we are just pushing this down a certain distance. Under output, I'm just going to go under here. And remember, when we're always doing nonlinear things, we specify, you know, how many times we want it to run. So in this case, we could say, hey, let's just put in a different number. Let's say like 51 times or 60 or whatever. And we're going to say user defined. And then we're going to say space them equally. So here we can see the results. Kind of pull down here. It's run 51 times, and it takes that and divides that over that period of time. So in this particular case, running this, and it takes about 25 minutes to run it. So I'm not going to run it here, but I have the results already done. But this is how we would set this up. It runs through it at each step, figures out the deformation, then applies the load to that deformed shape, and we'll end up what we're going to see here. So let's look at the results. And we'll take a look at looking at displacement. We'll say deform, animate that. So here we can see it. Again, remember, it's moving down that 5.8 millimeters, then moving back up. But we can see as this follows along, and these guys never ended up hitting the back of this. So I never really needed to put that extra contact in, but that's fine, right? Whether they come in contact or not, it doesn't, only when they come in contact, I should say, that it really comes into being used in the calculations. But here we can see the deformation here. We can see how this is behaving, and we got an accurate representation. And again, because it stays bent, it's a plastic analysis. But you can see all the different types of things that can be done using the advanced analysis package. A variety of different areas that we can cover. Hopefully these examples were a benefit to you. And just kind of summarize where this fits in the scheme of things. It's the advanced simulation extension. And we covered a variety of different examples of the different capabilities here. It is as simple as it looks, right? It allows us to use basically a nonlinear solver to solve, or use a linear solver to solve nonlinear situations and give you accurate results.